So now this brings us to the calculus portion of these 3 videos covering section 5.1, which is of course to find the derivative of the natural log function. The derivative of the natural log function is essentially 1 over x, and that follows from the definition of the natural logarithmic function as an antiderivative. So everything that we've been talking about, that would make perfect sense if the antiderivative or integral of 1 over x is the natural log function, then it would make sense that if I derived the natural log function, I would get 1 over x. So the second part is essentially just using the chain rule. So if I'm taking the natural log of something other than x, so something that has a derivative other than 1, then I would need to remember to take 1 over u, whatever that function is, but also times the derivative of u. So typically we're just going to write that as u prime over u because we're multiplying it by the derivative of whatever we're taking the natural log of. So let's take a look at some practice using that and just recall that the derivative of the natural log of u would be u prime over u. So that's what we're going to be using. So for instance, on this first one, the first thing I would do is say my solution is going to be 1 over 2x because we always take 1 over that value. And then I can multiply that by the derivative of 2x, which is 2. Now I don't need to write it as 2 separate steps like I have here. I'm just showing you where it came from. I took the derivative of the natural log, and then chain rule says also take the derivative of what we're taking the natural log of. And so of course what I end up with here is just 1 over x. And again, this is the way you would more likely write that work. Again, second one I'm looking at on my denominator, x squared plus 1. My numerator would be the derivative of this, which would be 2x. And so that's my final solution. Last one, x times the natural log of x. Don't be fooled. This is a chain rule problem. A product rule problem. So what I have here is the derivative of x times the derivative of the natural log of x. So remember, our product rule says we're going to take the first times the derivative of the second plus the second times the derivative of the first. Then of course I'm going to do the derivatives. So the derivative of the natural log of x is 1 over x. And so I just rewrote x. Here I rewrote natural log of x and then found the derivative of x, which is 1. So my final solution is 1 plus the natural log of x. So every once in a while we'll find a question where it's more convenient to actually use logarithmic differentiation, which essentially tells us to take the natural log of each side of our function and then use the properties of logarithms that we just learned. So let's look at an example of that. So let's take a look at this question, and by no means is logarithmic differentiation the only way I could derive this, because we have the strategies that we've already learned on how to find this derivative. But let's look at natural logarithmic differentiation as an option. So the first thing I'm going to do is I'm going to take the natural log of each side. That's step 1. So I've taken the natural log of y and the natural log of all of this mess, the whole thing. Now the purpose of that is so then I can use the properties of logarithms to reduce or simplify the right-hand side of my equation, because the left-hand side is pretty simple so far. But the right-hand side, I have a quotient, so notice I'm got the subtraction in between, and I'm using that power rule that says let's take the 2 and put it on the outside, and here this is really just a 1/2, so let's put that on the outside. And again, minus because it's a quotient. Step 3, I'm actually going to take the derivative. So I'm going to take the derivative of each side, remembering that the derivative of a natural log function, u, would be u prime, whoops, that's not supposed to be prime, u prime over u. So keeping that in mind, the natural log of y, I would then find y prime over y. Because I'm deriving with respect to x, we need to include that y prime in there. The next one I've got 2 on the outside, and then the natural log, or the derivative of the natural log of x minus 2 is 1 over x minus 2. The last one, I've got a negative 1/2 on the outside, and then the derivative of the natural log of x squared minus 1, plus 1, is that I put that on the bottom, the denominator, and then take the derivative and stick it on the top. So that was my next step. From here, it's algebra. We're just simplifying. So notice, and the step I didn't show in between here and probably should have, is I rewrote this guy as 2 and then x minus 2. And I rewrote this guy as x over x squared plus 1. And then what I did is I wanted to be able to write the whole thing as a fraction together. So I took this times x squared plus 1, and on top and on bottom, of course. And this times x minus 2 on top and on bottom. And that's what enabled me to write it as one fraction. And then I did all of this math sort of off camera to come up with all of this in my numerator. So there was a lot of steps in between, but it's just algebra, so I know that you can do that yourself. Now notice that I'm trying to get to the point that I find y prime, and right now I don't have that. I have y prime over y. So I'm going to take each side times y. Wow, what's going on with my pen today? I'm going to take each side times y, and that on the left side is going to give me y prime, which is what I wanted. And on the right side, it just gives me this y times everything. And I don't love that, because when I find my derivative, I want to find it in terms of just one variable. So notice what I'm going to do is I'm going to take this guy, which is what y is equal to, and I'm going to plug it in. So that's all I did here on this step, is to plug it in. And from there, I just did some simplification. So I noticed that I had an x minus 2 here, and an x minus 2 squared here, so really I just took one of those away. And then this guy was x squared plus 1 to the 1/2, and so I added that to x squared plus 1 to the first, and so that's where that 3/2 came from. So this is my final solution. Again, could I have found that using the quotient rule? Of course I could have, but it would have been just as long and complicated. So what I'd like you to do is now to find the derivative of each of these functions using logarithmic differentiation. So even if you can find the derivative in another way, I'd like you to use logarithmic differentiation for good practice. When you're done, press play to see how you did. So again, the first guy, I'm going to take the natural log of each side first. Notice natural log of y, natural log of all of this business here. I'm going to then simplify using my properties. So notice all I did was stick a minus in between, and that's all I had to do. Now I'm going to find the derivative of each. So the derivative of the natural log of y is y prime over y. The derivative of this is stick that on the bottom, put the derivative of x squared plus 1, which is 2x, on the top. Natural log of x, derivative is 1 over x. Again, plop that y to the other side, so times y times y. That gives me y prime. Plug the y back in. And then I could do some more simplification here. And who's to say what's right and what's wrong in terms of simplification. But obviously this could be simplified further. I just chose to leave it like this. For my second one, again, logarithmic differentiation. Take the log of each side first. Do your properties that says if you've got a 2, take the 2 and put it out front. This one, more complicated because I actually have a product in the denominator, so notice they both get a minus. So it's x and then minus 1/2 natural log of x plus 1. And from here, I'm just finding the derivatives of everything. So the derivative of this, y prime over y, again 2, the derivative of this, 1 over 2x plus 3 times 2. Derivative of this is 1 over x, derivative of this is 1 over x plus 1, again times that 1/2. And then simplify, if I can, a little bit, and take it times that y. And that y, again, is that original function. So this is my final solution. Again, could I keep simplifying this? Yes, I could. So just pay attention to how simplified we want the final answer to be. So this is kind of a fun little caveat into what we've been talking about, which is if I have the natural log of an absolute value of a function, it's really not going to change anything. I'm still going to just find u prime over u, and the reason that this works is of course because the absolute value function is defined for only positive numbers. So whatever happens here, that u is going to turn into a positive before I take the natural log of it, which means it's okay for me to use it because I can only use positive values with the natural log function. So for instance, if I'm finding the natural log of the absolute value of the cosine of x, so even though I end up maybe with some negative values when I find the cosine of x, that's okay. I've got the absolute value, and so the absolute value basically says I'm still using u prime over u, and u prime would be what's the derivative of cosine of x, which is negative sine of x, and then of course cosine of x goes in the denominator. And hopefully you're familiar enough with logarithmic functions to know that the negative, well, just sine over cosine is tangent, and of course because I have a negative, that's negative tangent of x.